So this is chapter 6, chapter 7. So I'm kind of skipping around. First off, I'm going to do some terminology. We're going to look at geminal, and this is in the term of alkyl halides. We can have two types, more than two types, but these two words are used. Geminal alkyl halides have two. I get the lights right? Yep. Two halogen atoms bonded to the same carbon. So for instance, it could be two chlorides. So those two chlorides, those would be geminal chlorides. Okay? So they're bonded to the same carbon, so geminal, and the other one is vicinal. And these are have two halogens, atoms, bonded to adjacent carbon atoms. So in this case, those two chloride atoms would be vicinal. Okay? If it looks something like this, those two chloride atoms are not vicinal. They have to be adjacent carbon atoms. So this is a dichloral, but a non-vicinal, a non-geminal dichloral. And the book uses this. We're going to see this when we're making we can make alkenes and alkynes from these. And having vicinal or geminal will be a term that's going to be used in the reactions. Also, I did do a lecture. Someone came in and missed the Newman projections. I did a lecture in my office and posted that under the date that was supposed to be. So the Newman projection video is up on Connor.
So can you have ions that are both geminal and
Yeah, you could have ones that, so for instance, something like so there's geminal, two bromines are geminal, and they're vicinal to one another also. It's a descriptive, okay? So that's just some terminology that will pop up every now and then, so I just want to go over that. So now we're going to look at our first real reaction. We talked about one type of reaction already, and that was radical chemistry. So we did some radical chemistry. Now we're going to do our first more controllable reaction. This is nucleophilic substitution. So if you remember from exam 1, a nucleophile is an ion or molecule. It doesn't have to be charged. That donates a pair electron. So I'm going to use Nu as a nucleophile, a generic nucleophile. I'm going to say this is a negatively charged. I have some alkyl halide, and this is just a monosubstituted alkyl halide, so H3C. I'm going to use X for my halide, so that could be a chloride, a bromide, or an iodide. I'm leaving fluoride off there on purpose. We'll get to that later on. But X is any halogen at this point in time. And basically, this is a substitution reaction. So the X is substituted with my nucleophile, and I get my negatively charged ion coming off. In this case, since it's a halogen, this is going to have a full octet. Okay, so nucleophilic substitution, I'm exchanging my halogen, in this case, for a nucleophile. That's a complete thing on a nucleophilic substitution. Okay? This X in nucleophilic substitutions has a special name, and it's called the leaving group. So my X is a leaving group of some kind. Usually we're going to use halogens. We do not always have to use halogens, but it's the most common one. Okay? And why would we use why would halogens be a good leaving group? What makes a good leaving group? They're electronegative. What does this have to be in order to be a good leaving group? It has to be stable. It has to be a stable ion. And you know, like if we have HI or HCl, that's a strong acid. It completely disassociates. We know these halogens are very stable by themselves. So having a stable leaving group is very important. Halogens make a very good leaving group. And we'll talk more about this in depth. So for instance, if I had, in this case, hydroxide, and I reacted this with methyl bromide, this undergoes a nucleophilic substitution. I'm just exchanging the Br in this case with an OH. So in this case, I'm going to make methanol plus, I'll have Br minus floating around. Okay, so we're just substituting our nucleophile. In this case, it's hydroxyl is my nucleophile, and I'm substituting the bromine for that. It doesn't, like it says, it doesn't have to be an ion. It could be a neutral complex, in this case ammonia. So let's switch up a CH3I. So in this case, iodine will be my leaving group. I'm going to substitute the iodide, in this case, for a ammonia. This is going to make an ammonium salt. This will have a positive charge. And I'll have I as my leaving group. This will be a negative charge. The charges always have to balance out. I started with zero charge in the reactant. I have to have an overall zero charge on my product. So both of these are nucleophilic substitution, one with an ion, an anion, and the other one is a neutral compound. Okay? So there's two types of nucleophilic substitution, and we're going to go over in depth. So the first one we're going to talk about is an SN1 reaction. So the S in this case stands for substitution. The N stands for nucleophilic. Running behind my, gotta bring it down, so there we go, nucleophilic. And then 1 means this is a unimolecular reaction. What does unimolecular mean? The rate, one molecule, very good. So the rate determining steps based on one thing, okay? So now we're going to go, so that we know what a nucleophilic substitution is. I'm going to draw the mechanism for how this occurs. So there's my alkyl halide. My I is going to be my leaving group. So this is where the curved arrow formalism comes in big time. We're going to be using this a lot. So curved arrow formalism, the first thing that happens in a unimolecular reaction is that the electrons that are between my carbon and my leaving group, in this case the iodine, completely go on the iodine, and I form I minus plus this carbocation. Okay? This is the slow step in this reaction. So we talked about reaction mechanism, drawing the energy diagram. Loss of the leaving group is a slow step in the SN1. So the rate determining step, or the unimolecular step for this reaction, is the loss of the leaving group. Okay? So this is a first order reaction. The reaction is depending on how fast that iodine can come out there. Okay? What is the geometry of that molecule? Tetrahedral, right? So this is a tetrahedral, which is sp3. What's the geometry of my carbocation in this case? Trigonoplanar. Okay, so that's very important. Did I spell planar? Oh, planar is misspelled. That's planner. Okay, so this is very important. So I'm starting off with a tetrahedron. Okay, the bond angle for a tetrahedron is 109.5. So here's my leaving group in this case. I put hydrogens there so I didn't have to build a big model. This is leaving first, okay? Once that leaves, the miraculous thing happens. The carbon atom switches from a black color to a brown color. I just didn't have any black ones that were trigonoplanar. So now I'm forming this flat trigonoplanar, okay? So that's very important, because now when the nucleophile comes in, what side is the nucleophile going to attack from? Either side, okay? It's flat, so I have a 50-50 shot of attacking from this side, here's my OH, or from this side, okay? So that's a very important step in the SN1 reaction. I form an intermediate that's trigonoplanar, and I can get attacked from either side, okay? So the next thing that's going to happen, let's say my nucleophile in this case, I'm going to have this, since I had an OH there, here's my nucleophile. Now my nucleophile can attack from either side in this case, okay? Does it really make a difference what side it attacks in this one? No, it'll actually be the exact same thing because that's not a asymmetric carbon we're attacking to. It will be later on. So these electrons attack at that carbocation to form an oxygen-carbon bond. This is a fast step. So I'm going to form, in this case, this alcohol. And again, I just go from tetrahedral. My intermediate is a trigonoplanar. I can attack from either side, and then my product again is a tetrahedron. Okay. From my mechanism here, draw the energy diagram. You should all draw an energy diagram pretty straightforward. So my energy diagram is going to look something like, again, there's my energy position of atoms. Does this say most of the time these are exothermic reactions? They're not always, but this say it's exothermic. I start with my reactants. I should put OH over here too as my reactants. The first step is going to be the slow step. I form a carbocation intermediate. The second step is fast. Then finally I form my products. Okay, so that would be my energy diagram, or the profile of energy diagram roughly, okay? First step, the rate determining step, unimolecular. I form some intermediate. In this case, the intermediate is carbocation intermediate. I got positive and negative charge. That reaction goes very quickly. A low energy, a smaller second peak, and then I finally form my product. Okay? Questions on that? SN2. You guys are a smart class. S stands for? Very good. N stands for? Nucleophilic. 2 stands for? Bi. Okay. So in this case, the rate determining steps determined by 2 things, okay? In SN1, the rate determining step was always determined by the loss of the leaving group, okay? In an SN2, it's slightly different. Okay, so let's go through the mechanism on this again. So in this case, I'm going to have, let's just stick with iodide. And I switched from CH3s to H's for a reason. I'll get into that a little later. Let's use the same nucleophile. So on an SN2 reaction, what happens on an SN2 reaction is that as the nucleophile is attacking my carbon, the leaving group is leaving at the same sort of time. Okay? So I'm going to try to draw a picture of what the transition state is. So the transition state looks something like this. So as the one bond is forming, our other bond is breaking at the same time, okay? So for an SN2 reaction, the attack of the nucleophile and the loss of the leaving group play a very important role. Both of those things tell tell us how much energy is needed for the rate determining step, okay? So this is a transition state. And finally, I end up, through that transition state, I end up with my product. Again, methanol in this case. Important things to take from this is that the nucleophile always attacks from the opposite side that the leading group is going away from. And I think in the book they use, you take an umbrella, you invert the umbrella coming in from the other direction. So the nucleophile is always attacking from the opposite side that the leading group is going off of. Okay? So that's very important. If I drew, and say this is an exothermic reaction again, draw the energy diagram for this mechanism. So in this mechanism, how many intermediates do we form? How many intermediates do we form? 0. There's no intermediates formed. Okay? There's just our reactants. They hit the transition state, and we form the products. Okay? So we do not have any intermediates. We just have, in this case, one transition state, and that transition state is the approach of the nucleophile as the leading group leaves. Okay? There are no intermediates formed in an SN2 type reaction. Oh, thank you. That's a good point. On all mechanisms, you don't get rid of anything, okay? You should always have all the stuff I started with my reactant should end up in my product, okay? When we start actually doing reactions, I'll only be interested in the organic product, but I'll tell you that when we get to them, okay? Questions on that? Brad?
Does the nucleophile kind of get an opportunity to attack the carbon because of dipole moments?
Yes, sort of. It's important. It's an important part. There's several things important. Because you got to realize that iodine is more electronegative. So the most positive portion of that molecule will be the carbon in this case, right? Because the electrons are closer to the iodine. Okay. So there's another question. I thought I see that right hand. Yeah, it's Duncan.
So the two things the rates depend on are how fast it can get attacked by
Yeah, so how easy it is for the leaving group to leave and how aggressive the nucleophile attacks. Okay? So now we're going to look at some of these factors. So there's a bunch of different factors. Yes, Nico.
Do we have to know about Walden inversion for SN2?
What's that?
Do we have to know about Walden inversion for SN2?
I don't know what Walden inversion is.
Like the flipping the umbrellas with the...
Yes, you will have to know that. I've never called it Walden inversion. So let's go with this. So let's say I have this molecule here. Okay, I have that molecule there. I'm going to react it, and most of the time, they just won't put the nucleophile there. So in this case, I'm going to put sodium hydroxide. We know sodium hydroxide is a strong base. It's going to completely ionize. So therefore, the nucleophile in this case will be the OH. So the nucleophile in this case, so the first thing you have to do, what is the nucleophile? In this case, the nucleophile is OH. Michael?
So, real quick, for general compounds then, how does that work with that?
We won't have any substitution in it. We won't do any general substitutions for a while. But we will get to those, but not right away. We're just going to look at mono substitutions at this point. One leaving group leaving, one group coming on. Other question? So the first thing you do in any nucleophilic substitution, you have to determine, if you can't determine the correct nucleophile, you're sunk in the water. So determine the nucleophile. In this case, the nucleophile is OH. Next thing we have to determine is, what is the leaving group? And the leaving group in this case is going to be the bromine. So the reaction is going to happen at the carbon attached to the bromine. Okay? There's one more thing to worry about, and we'll get to this. If we look at that, how many stereocenters in my reactant, my organic reactant? One stereocenter. So if this was an SN2 reaction, so if this went by an SN2 mechanism, what would be my product? If everything's drawn exactly the same, my nucleophile is attached to there. Is my nucleophile going to be coming out of the board or into the board? It's going to go into the board. It has to attack from the opposite side that the leaving group's on. So an SN2 reaction, we're going to get one product, and that product is always going to be the inverse of what we started with. Okay? Now, if I did the same reaction, tweaked the conditions a little bit, and used an SN1 mechanism, how many products am I going to form with a stereocenter? It will be two, because we formed that trigonoplanar intermediate. So I'm going to get a mixture of the enantiomers, and I'll get a racemic mixture, a 50-50 mixture of both the R and the S. Okay? So I get different products depending on what mechanism track my reaction goes down. Okay? Questions thus far? Michael?
So for the SN2 reaction, does that mean that if the reactant is an S, it'll turn into an R?
Yeah. So for an SN2 reaction, okay, first, we should be able to figure this one out. Is there product R or S? You guys practice all Tuesday, right? On R and S. This is definitely R, right? Everyone sees that, and it just comes naturally. You just look at it, and it just pops in your head, R. Whoop, R. Okay, that is an R. Hopefully you got that in R. And for an SN2 reaction, it always switches. So if it started off in R, it should be an S. Yeah. I mean, as long as my nucleophile has a higher priority, I mean, the same thing. If it happens for this class, I can make it so it's not, but usually it's going to flip from R to S. So in their case, I get an R and an S. I had a question somewhere here, I just ignored it. Okay, that worked. So I'll ignore more questions from here on out. Okay, so we have to determine multiple things in nucleophilic substitution. We have to determine the nucleophile, we have to determine what our leaving group is, and then we have to determine, do we have a stereocenter? Because if we didn't have a stereocenter, let's just do one without a stereocenter. Plus, let me just change it up a little bit. See how good you guys are. Here's my new nucleophile. So my nucleophile in this case is going to be what? OCH3. So my nucleophile in this case is what's connected to my sodium, OCH3. So that's what I'm substituting. And my product is going to be this for which of the mechanisms? Who says SN1? Who says SN2? You're all right. Right? Because is that a stereocenter? And the BR. No, so inversion doesn't matter, right? We can just flip it over. So those two are actually, would be the same as an OCH3. So we have to make sure we have a stereo center first. If we don't have a stereo center, SN1, SN2 really doesn't matter a lot, okay? So we have to determine we have a stereo center because inversion on this doesn't mean anything good. We didn't start with an R, we can't invert that to an S. We start with nothing, and we end with a different nothing. Yes? Someone said something.
I asked, so it's line.
Yeah, so this SN1 and SN2, there's only one product in this case because there's no possibility of RMSs in this case. Okay? Sarah,
So with that, how do you determine if a reaction is going to be an SN1 reaction or an SN2?
very good question, Sarah.
Sorry.
Okay, you guys are going to figure that all out. So this is where I stop teaching and you guys start teaching me. Okay, so let's just start with a primary alkyl halide. Whoops. Jordan, are you here today? You thought I'd forget your name.
Yeah, you kept forgetting it.
No, until who just pointed it out. Oh, it was Maddie, Viking Maddie. Thank you. Yeah, she's not here. She skipped. -1 point for Viking. You can tell her that, Jordan. Payback. Primary alkyl halides. What would you think they would go by and why? What would be best? So first off, let's just come up with a primary alkyl halide. Let's just do this one. What's the difference between an SN1 and an SN2? What happens in the SN1? I form an intermediate. What's important? We need a stable intermediate. Our primary carbocation is stable. No. Okay? For an SN2 sort of mechanism, what's needed? We have to, what? What happens in SN2? The nucleophile attacks, the leading groups leave. So what do we need a lot of? The final frontier. Very good. Okay, we need a lot of space. So for a primary, there's lots of space. The hydrogen takes up a little room, and then the alkyl is on one side. And it gives a lot of room for an incoming nucleophile. And we know primary carbocations are not very stable. So in this case, primary alkyl halides usually go by an SN2 mechanism. Okay? And this is due to two things. Due to the lack of stability of the primary carbocation. And minimal steric hindrance. Minimal steric. That's a fancy word for space. It has space to attack. The nucleophile has space to attack. It's not hindered by large, bulky groups. Okay? So that is primary alkyl halide. So if you have a primary alkyl halide, these, for this class, will always go by a SN2 mechanism. So if I see it's a primary alkyl halide, I know I'm going to go by SN2 mechanism. Do we have to worry about inversion for primary alkyl halide? Why not? Because it'll never be RS. If it's primary, there's two hydrogens on there, it can never be R and S. So we don't have to worry about that. So let's go to the other end of the spectrum. Tertiary alkyl halides. So let's do that one. What would you think tertiary alkyl halide was preferred? SN1, why? More stable intermediate. Tertiary carbocation is a lot more stable than a primary one, okay? so it's more stable, okay? Secondly, it actually, with all these different groups around it, right now I just put methyl group, but if I put like, to just make this more exotic, okay? So now, the bigger those groups are, the harder it is for my nucleophile to attack from the back side and as the leaving group's leaving, okay? So this inhibits the approach of the nucleophile. So for the most part, tertiary alkyl halides, so they usually go SN1 mechanism. And this is due to the stability of the tertiary carbocation and steric hindrance of the groups attached to this thing. So the larger those groups are, the less and less probable for an SN2 reaction to occur. Now we can actually get tertiary alkyl halides to go by an SN2 mechanism. Okay? I can force a reaction, I can make the group small, add a lot of energy, I can make this happen. For this class, well, tertiary alkyl halides will only go by an SN1 mechanism for my exam. Okay? Can we make primary go by SN2? I mean SN1 possibly. Can we make tertiary go by SN2? Most definitely, but I'm not, those are exceptions to the rule rather than the rule. Wayne.
Is tertiary more stable because the charge is more dispersed?
So it's similar to why the radical, remember the radicals were more stable, tertiary radicals were more stable than secondary and primary. It has to do with those electrons around that can kind of backfill into that positive hole that we have in the molecule now. Any other questions? And we're going to talk about all this more in detail in a little bit. So the last one, group, there's only primary. How many quaternary alkyl halides do we have? Only in Texas. Very good. So we don't have any of those. So secondary alkyl halides. Secondary alkyl halides can go by either an SN1 or an SN2. Okay? So these are kind of in the middle. We know secondary alkyl halides or carbocations are not quite as stable as tertiary, but more stable than primary. So we can go by an SN1 mechanism. Plus, depending on what the size of the groups are, the steric hindrance is a lot less than the tertiary one. So secondary alkyl halides can go either by a primary or secondary. And there are things that play factors that we'll talk about in a little bit. Questions thus far. So this is just kind of an overview. We're going to do lots of reactions. I'll give lots of examples here probably on Friday. So we're going to look at the effects of different parts of this reaction. So the first part of the reaction we're going to look at is the nucleophiles. And we know nucleophiles donate an electron pair. And here's some rules for nucleophile species. With a negative charge are stronger nucleophiles than similar neutral nucleophiles. And the key here is similar. So if I asked you, for instance, water can be a nucleophile, right? It has a pair of electrons it can donate. And I asked you, which one's a stronger nucleophile? The negatively charged one or the neutral, similar one? You would say the negatively charged one. So the stronger nucleophile, in this case, would be the OH minus. Okay, so similarly charged if it has a negative charge, it's going to be a stronger nucleophile than the neutral species. There's a new word for you, nucleophilicity. I don't know if it's a real word, but I can spell it any way I want when I make up my own words. Decreases, so that's the strength of the nucleophile. So nucleophilicity is the strength of the nucleophile. Decreases as you go left to right across the periodic table. So in this case, if I had an OH minus, so let's do a hydroxyl versus fluoride atom, which one of those would be a stronger nucleophile? Charges are the same in this case. I have to leave the charges the same. In this case, so I have to go from left to right. The strength of the nucleophile decreases. Therefore, OH would be the stronger nucleophile. Why is this? Electronegativity. The fluoride's hanging on to its electrons. It's holding its electrons tight. It's more electronegative. The oxygens are not held as tight. Remember, a nucleophile wants to donate the electron. So fluoride atom has those electrons to donate. It doesn't want to. Okay, they're mine. Okay, so if he doesn't donate as much, he will donate them, but he's not as strong a nucleophile as an OH minus. Okay. Questions? We're still on nucleophiles, nucleophilicity. I think this is actually in your books. I don't think I made it up. I'm not that smart. Increases as you go down the periodic table. Okay, this is due to the increase in the size of the atoms because the larger the atom, the more polarizable it is. So, iodine is a better nucleophile than bromide, which is a better nucleophile than Cl, which is a better nucleophile than fluoride. If I ask you which one of those is the strongest base, in gaseous phase, which is the strongest base? F minus or I minus? F minus is the strongest base, okay? So the thing is, this does not only hold true for nucleophility increases as you go down the periodic table. If the solvent I'm doing the reaction in is a protic solvent. So this is for protic solvent, and protic means it has an OH group on it, okay? It has hydrogen bonding going on. In an aprotic solvent, it's just the opposite. Fluoride's a better nucleophile than Cl, which is a better nucleophile than Br, which is a better nucleophile than I. And this has to do with some solvent effects, and we'll talk about these in a little bit. So, if it's a protic solvent and it's a strong base, and there's hydrogen bonding going on, what can happen is my solvent can form like onion layers around my strong base, in this case, let's say fluoride. It can form onion rings, so that makes the approach of my carbocation to my nucleophile, and inhibits that, okay? So if it's too strong of a base, it actually, the solvent works against it, okay? So if we had an aprotic solvent or something that didn't have hydrogen bonding, it's just the opposite strength of the nucleophile. And this will play a very important role in secondary. So we'll see these solvent effects in our secondary alkyl halides, okay? So solvation, by protic solvents, and for this class, protic solvents are going to be those solvents that have a hydroxyl group, impedes nucleophilicity. Questions? Whoops. So, protic solvents or aprotic solvents, what do you think would be better for an SN1 sort of reaction? What's the key in SN1 reaction? We need a very intermediate. What would help stabilize our carbocation? A protic solvent or an aprotic solvent? Protic solvent. A protic solvent, just like for a strong base, like F, it can form these rings to kind of help stabilize our anion, or in this case, the carbocation. So protic solvents favor SN1 type mechanisms due to stabilization For an SN2 type reaction, no carbocations are formed. So actually, since the protic solvents impede the strength of our nucleophile, for SN2 reactions, we need, so, do SN1 reactions need a strong nucleophile? No. Why not? Because we have a carbocation already, so we can actually use weak nucleophiles to attack. For an SN2 reaction, do we need strong nucleophiles? Yes, because the rate determining step in that case is depending on the strength of the nucleophile and the loss of the ligand group. Okay? And since protic solvents tend to weaken or impede the strength of our nucleophile, for an SN2 reaction, having an aprotic solvent is favored. So aprotic solvents favor SN2 type mechanism. Questions? So going back a couple pages, so we had secondary. Secondary alkyl halides can go via SN1 or an SN2 type mechanism. So if we figure our alkyl halide isn't secondary alkyl halide, the next thing we need to look at to determine if it's going by an SN1 or an SN2 mechanism is to look at the solvent we're doing the reaction in. So if that's a protic solvent that we're doing the reaction for a secondary alkyl halide, it would be a SN1 mechanism. If that's an aprotic solvent, it would be an SN2 mechanism. We'll continue on with this on Friday.